So now let's have a discussion on Ampere's circuital law. Now Ampere's circuital law can be understood by a special case of Biot-Savart law. Biot-Savart law. So what we can understand is, say suppose the surface has current passing through it. Say suppose there is a surface. Say suppose this is my surface. And in this surface there is a current that is being passing through it. Now let us consider this particular boundary. Say suppose this is a surface. For your convenience, let's suppose this is a surface. Now on my surface, this is the current that is being flowing. So let this boundary be made up of very small elements, say dl. Small element dl that we can consider. Now what we will take is, we will take the tangential component of the magnetic field. If you take the tangential component of the magnetic field, then we know that B tangential into dl is your B dot dl. If I am just taking the tangential component. So in a way, if you look at the magnetic field, what happens is that this is a current that is being passing. So we will be considering only the tangential part. So now, if for every small element, say suppose this is dl and this is I. For this is dl and this is I. For this is dl and this is I. So for every small element, we are just considering the tangential. If you are considering this part, say suppose if you are taking this part, then this and this gets cancelled out. So we are only taking the tangential part. So now the overall, if you look at the overall sum, that is it, the sum then tends to an integral. Then this sum tends to an integral, and this Ampere's law states that this integral is equal to mu naught times the total current, mu naught times the total current passing through the surface. Passing through the surface. So in a way, if you want the electric field, this is given a B dl is equal to mu naught times the total current, and this is known as your Ampere's circuital law. Ampere's circuital law. Now, where I is the total current through the surface, this I is the total current through the surface, the integral is taken over a closed loop coinciding with the boundary C of the surface. So we are taking a closed loop. We are always taking a closed loop, and we know in a closed loop what we had was B is equal to, now we in our previous discussion we had B is equal to mu naught I upon twice R. This is mu naught I upon twice R. So this was my B. So this can be regarded as dl. dl is what? Integration dl is twice R. So we can compare this particular result with this particular result. Now if you try to understand the direction of your magnetic field, what you can do is, you just have to curl your fingers along the surface where the current is flowing. So curl your fingers along the surface, and the fingers should be pointed where the current is flowing, at which direction your current is flowing, and the direction of your thumb. Now we are talking about your right hand. This is known as right hand thumb rule. So right hand thumb rule states that if you curl your finger on the surface along the flow of current, then the direction of your thumb gives you the direction of the magnetic field, and this is known as right hand thumb rule. And this particular equation is known as Ampere's circuital law.